Right now, how good. Yeah. Not only that, it was the key to the layman. So say, you know what? Good in a training. Cannot understand it. Also, there are a lot. They get. Worker was not in. Does it agree? However, there is just now the out, so maybe it's easier, but in French, well, get
Good morning, everyone. I think it's time to start the session of the day. Thank you, everyone, to come, the courageous ones at 8 in the morning here. So the session today is about multiferics, and the first speaker is Dr. Xifan Wu from Temple University, who will talk about the BFO-like structure in superlattice.
Okay. Okay, good morning, everybody. Today I'm talking about my recent work, which we done with many collaborators. Oh, by the way, first, thanks for the organizing committee to invite me here, and this is my opportunity to give the second talk in the Ferroelectric workshop. The first talk was 11 years ago. I still have the slides. Okay, so today I'm going to talk about how to stabilize the so-called barren bismuth ferrite phase in the oxide perovskite oxide with rotation in general. So in today's talk, first I'm going to talk about the distortions, in particular ferroelectricity distortions, and its connection with autohedral rotations. Second, I want to point out that there is a bismuth ferrite phase, which is a metastable phase for many perovskites, and the answer is we can stabilize this phase for larger polarization. And how to do that, we discuss. Actually, our conclusion was simulated by the BTO, CTO superlattice we learned from there. And then I will give some predictions for new ferroelectric materials based on the concept we learned. In the end, I will try to give a short summary on the interface approaches so far we have in the market. Okay, so first, what's the distortions in ferroelectricity? So we know that perovskite is simple. And also it's important because it has many distortions. Many are functional distortions. For example, the barium titanate has this gamma point distortion related to the ferroelectric motion with cation and anions separate, give a dipole. If you want to understand the origin of the distortion, it's coming from a gamma point instability for the cubic barium titanate. Fortunately, for barium titanate at room temperature, the ferroelectric distortion is a major distortion developed at room temperature, P4MN phase. However, it's not generally true for every perovskite. In many perovskites, we have the octohedral rotation network. We have patterns of octohedrals. For example, in general, you can have a rotation around 110 direction. Octohedral rotation. You can have another rotation around 001 direction, and this is 110 direction. For 001 direction, for simplicity, we often call it rotation, and for 110 direction rotation, we call it tilt. The typical materials have this rotation pattern is a calcium titanate, for example, with a PBN phase. And we also know that if you want to try to understand the origin of the rotation patterns, it actually originated from the Bredon zone boundary instabilities. For example, the in-phase rotation is from the M point, out-of-phase rotation tilt is from the R point. For a long time, in the calcium titanate-like, CTO-like materials, we realized that when we have such a pattern of rotation, actually the polarization is suppressed. This is generally observed in calcium titanate-like materials, and I think this is also, this phenomena is also proposed by David Van Buren and John in almost 20 years ago, and in which they found there is energy competing terms for the rotation and ferroelectricity. This effect was recently revisited by Craig Fanney and Nicole Benedek, and they found that in addition to the in-phase rotation and tilt, this distortion pattern allows the X-point mode, which is antipolar distortion, to develop. Once this antipolar distortion develops, then the ferroelectricity, of course, is suppressed. Okay, so this is one pattern of autophagy rotation. We know that not only one pattern, we have other patterns. For example, if both your autophagy rotation originated from R point, for example, in the bismuth ferrite phase R3C, we can understand this structure by an out-of-phase rotation around 001 direction and tilting. Tilting is the same. They both originated from the R point instabilities. We know that, of course, barren bismuth ferrite also promote very large polarizations. Combined with other properties, for example, the high near temperature and large polarizations and large transition temperatures of Curie transition temperatures, bismuth ferrite, BF4, has been studied intensely in the last 10 years because it's highly functional materials. Then the question is, for bismuth ferrite, the structure like bismuth ferrite is so rare in the nature, and we have a lot of materials who has the CTO-like structures. Then can we change between the two structures to get larger polarization? The answer is, of course, yes. However, we learned indirectly in another way by studying the superlattice from BTO, CTO. Now I'm going to talk about the series of works. We try to model the superlattice structure of BTO, CTO. Why we want to understand the superlattice? The interest comes from the experiments, actually. Why the experiment is so interesting? Because Hongyang Li and Paul Evans in Wisconsin Madison, they have two individual measurements. One is on the ferroelectricity polarizations. The other is on the piezoelectricity. So what did we learn from the experiment? We learned that for a BTO, CTO superlattice, at short period, BTO, CTO, they have pretty large polarization. In another superlattice, 2 BTO, 4 CTO, so CTO is Ferroelectrics without any piezoelectricity, they observe a huge piezoelectric constant, 54, and comparable to the strained BTO. So this is so surprising. So why this happens? Of course, at that time, this density functional cannot reproduce the experiments. Actually, it takes us a while to understand and complete the structure inside. If you are patient enough, if you model all the distortions inside, step by step, for example, the ferroelectric distortions, autophagy rotations, and autophagy tiltings inside, and let the density function minimize the total energy, then you will get a large polarization at a short period, and you will get very similar piezoelectric constant comparable to the experiments scared by the BTO films. So my student finished this calculation 2 years ago, 2013, this time, 3 years ago. Then he pushed me to publish a paper. I said, not yet. We have not understand the complete story yet. We need to do more to understand it. Why it's difficult for me to understand? Because expected from bulk properties, the calcium titanate is a peroelectric, and the piezoelectric constant of bulk calcium titanate is essentially 0. So why we should have large, these two experiments indicate there is a strong ferroelectricity unexpected. Okay. Then what we should expect from the bulk properties? If the bulk properties can predict the superlattice properties, then we can actually predict the properties based on the so-called dielectric snap model. This model comes from first proposed by Jeff Neaton. Essentially, you need to consider correctly the electric boundary conditions in which for insulating superlattice, the charge is continuous in the z direction. So you consider charge continuity by applying the constant d features. Then you can build the superlattice by knowing the polarization. This polarization can be local decomposition or can be one-year-based layer polarization as a function of d. Then you can build the dipoles based on the knowledge of bulk information, and eventually you can get everything out for the superlattice. The bulk can be many bulk. Then if it works, you will get the blue line. It's far below the actual DFT calculations. So what does it mean? It means that simply the interface effect cannot be neglected. Then what is the interface effect? Okay, so in order to study the interface effect carefully, we carry out a new calculation based on 6 by 6 superlattice calculations. And after the calculation is done, we decompose the structure, the DFT structure, into many distortions. For example, in-phase rotation, which is typical for the calcium titanate structure, out-of-phase rotation, which is typical for bismuth ferrite, and also in-plane polarization, out-plane polarization, A-side displacement, and tilt. So we try to understand the picture slowly. So how we can understand? Far away from the bulk, far away from the interface, we look at the bulk calcium titanate. We can see that it is actually dominated by the bulk calcium titanate effect. You see a large in-phase rotation. You see 0 out-of-phase rotation. You see a large tilting mode. According to Nicole's recent studies, you can see that if in-phase rotation and tilts are developed, there is a large zigzag antipolar mode. This antipolar mode suppresses ferroelectricity. Okay, so this is bulk effect. And there is also an in-plane polarization. This in-plane polarization coming from the string-induced effect. This is also published by Karen Rabe and his student. If you apply an epitaxial string, then you will see a polarization develop in the 110 direction. So this is bulk region of calcium titanate. Then we look at the bulk region of barium titanate. It's very boring and also very interesting, clear. It's dominated by the bulk effect of barium titanate. You see no distortions along 110 direction, no autohedral distortions, and okay. So if everything is dominated by bulk effect, you will expect to see this line around 20 in the z direction for polarizations. However, you see around 28. Questions? So this effect must coming from the interface regions. Then what happened in the interface? Interface, we look at the interface region in the blue ones. What do we see? We see a suppressed in-phase rotation. We also see a suppressed tilting mode. Because this is too suppressed, we expect the antipolar modes also suppressed. Then what's new? We induce large out-of-phase rotations, which is typical for barren bismuth ferrite. And we also see an enhanced polarization around the 1 mode directions together. So due to this interface effect, this polarization along O1 direction, which measured by experiments, by the way, 1 mode O1 direction, is enhanced. Actually, the structure of a calculation is confirmed, partially confirmed by our experimental collaborators. These experiments by Jianguo Wen and Dean Miller in Argonne user facilities apply this fancy amplitude contrast-based TEM image, and they obtained the images. For example, these dark regions, the strong dark is barren. This line is TiO2 plane. This line is CaO plane. So this is the Ti atom surrounded by 2 oxygens. And on the right-hand side, we give the TM our DFT relaxed structures, and it is simulated another image. You can see that qualitatively very similar, but quantitatively, of course, slightly different. Then what is the qualitative information in this image? Actually, it tells you that the titanium O2 sandwiched between 2 BRO plane is flat, means there's no tilting, no autohedral rotation, etc. And also, this is kind of expected because barren is kind of large. BTO is kind of large tolerance factor. In the bulk region 1, calcium titanate, you see a large tilt. This is the alteration tilt due to the alteration rotations. If the TiO2 layer is sandwiched by 1 CaO and 1 BaO, you see the tilt still there, but largely suppressed. Okay, so the consistency gives us confidence that our DFT calculation is correct, and all this reconstructure seems to connect to the fact that there is a tilting, autohedral rotation, suppressed a little bit moderately on the interface, give this out-of-phase rotation, and which is characteristic of a BFO phase. Then let's try to understand why this happens. So in this section, I will discuss a modeling based on the model Hamiltonians. So we have calcium titanate, for example, grow on the strontium titanate. And we know that the BFO structure is also a metastable state of calcium titanate. Then we can expand energy. First, we expand the energy of CTO like in calcium titanate. This is a ground state. Expand by the distortions. This is the typical distortions to the 4th order. Then we can input the DFT energies and fit the coefficient, and we get many coefficients. By the way, it's interesting to point out this one is actually the trilinear coupling used in the, this is a trilinear coupling on the basis of the so-called hybrid improper ferroelectrics. And this term also proposed before by Nicole and Craig. You can see this term is a large negative time constant, a negative coefficient, which means that this term wants to lower energy to stabilize in this so-called antipolar modes. Okay, then we can do the same thing for the metastable phase of calcium titanate, which we call the BFO-like phase. In BFO and CTO-like, the difference is only in the rotation. One is in phase, the other out of phase. Again, we see a large term in the end, which is a full linear, full terms coupling term. Actually, we are not also the first one to realize the full linear coupling term is realized by David and Karen in a paper several years ago. And there is a corresponding large coefficient, negative coefficient, means that if this happens, the energy will be lowered significantly. So we have two energies and we fit the coefficient. Then we have the functions. Then what do we do? In experiments, we observed that what we do actually we suppress moderately autohedral rotation and tilt. So naturally, we can consider rotation and tilting can be adjusted by experiment conditions. Then we can define the enthalpy functions by minimize the other guys and keep rotations as controllable parameter. Then we got two enthalpies. In order to study the phase instabilities, we do the subtraction and we plot it. And what do we get? Oh, we get a very interesting plot. So this phase diagram, this plot tells you the phase instabilities, the competing phases between the CTO-like and the BFO-like phase, both in CTO structures. This yellow plane is the zero plane. If delta E is larger than 0, then CTO-like is stable because CTO is smaller in energy. If delta is smaller than 0, then BFO-like phase is stable. This is a natural ground state at this up point. You can see that when the rotation angle and tilting angle is fixed at experimental ones around 12 and 8, you will recover the recover DFT ground state. Then how we plot rotations as an order parameter. So in-phase rotation and out-of-phase rotation have the same order parameter. Now what happened is, when the rotation and tilt suppressed, in particular the tilting was suppressed moderately, we gradually comes into this region. In the plot, we also project the colors to represent the amplitude of ferroelectric mode. You can see that we can gradually go into the BFO phase when rotation and tilting is smaller enough. However, it's not 0 yet. So this tells you that we can understand our previously observed problem is actually the suppressed rotation and tilt on the interface help to stabilize the BFO phase. And again, it's not only that, because the term in the BFO phase has a full linear coupling. The ferroelectricity in the z direction and the ferroelectricity in the xy direction also helps. So we claim that our electric and mechanical boundary condition also help, because mechanical boundary condition is epitaxial strain induce a little bit in plane polarization, and electric boundary conditions applied by the BTO also help to push a little bit of the polarization along z directions. So this is the important information we learned for the design rule. If we suppress a little moderately the rotation and tilt, then we probably can recover or to stabilize the BFO phase, which is highly functional phase. Then what we can do further? We actually can predict new ferroelectric materials based on these design rules. Then what do we do? I demonstrate, we have many materials. We select like 4. We generate ferroelectricity based on non-polar materials, based on the rule we learned, based on the concept we learned from this project. Okay. Then what do we do? We first select the cubic-like structures, for example, the barium SNO3 and calcium barium liquinate. In this structure, there's no rotation and tilting, nothing. And also, there's no polarization in any directions. So it's just very boring structures. In the second material, we select a highly CTO-like structure in which the tilt, where is the tilt? Yeah, it's here. Tilt and rotation is pretty huge. Because the in-phase rotation and tilts, antipolar develops and suppress electricity, ferroelectricity. So there's no ferroelectricity in any directions. Okay. Then you combine these two together to make a 1x1 superlattice on any substrate. We can see that, the rotation pattern changes. We have out-of-phase rotation came out with a tilting. The in-phase rotation is completely gone. And we also have a non-zero polarization in 001 and 110 directions. And if you look at the numbers, the 110 is roughly square root of 001 direction, which means that the total polarization is roughly along 111 direction. So we can notice that for BFO is exactly along 110 direction. There is a symmetry breaking due to the superlattice here. And also, from the last two examples we have using different substrate, we can see that the substrate doesn't play important role here. Because we relax the structure by different substrate and we get essentially very similar results. Okay, so this is one demonstration we then in the end we want to summarize the available interface and at least available interface approach I know in the literature. We have three major interfaces. One is a tricolor superlattice proposed by Nassai and David Van Wilt more than 10 years ago. And the other is hybrid improper proposed by Craig and James and Nicole Benedek recently. And the other current one, what's the difference? I think both 1 and 2, they break inversion symmetry on purpose. So this is tricolor. By tricolor design, you can break inversion symmetry and tilt the double wire potentials, you get large polarizations. Then what's going on in the hybrid improper? Hybrid improper actually using this term, this triennial coupling term. In hybrid improper, you have two different bulk materials, have two different coupling constants, have two different antipolar mode. This antipolar mode doesn't cancel on the interface, give you a non-zero polarization. So this is what's behind the hybrid improper. In the current proposed method, we actually try to change the energetics of the distortions, try to reshuffle the distortions, and make a transition from the CTO-like structure to the BFO-like structure. For future work, I think, the example we demonstrate, of course, is very interesting. However, we know that the polarization has not exceeded bismuth ferrite yet. It's not huge, but for future work, I think it's important to turn the other rare earths iron oxide. For example, many orthorhombic has pretty high transition temperature, near transition temperature, but no ferroelectricity. Maybe we can turn these materials into room temperature multiferroics. In the end, I want to thank my collaborators, Hongwei Wang, which is a very great student who worked with me for all these years on this project. He managed to do 10 times amount of work than he originally proposed. Then Jian Guowen is the guy who behind the TM experimentalist. And in the end, I want to thank Dave Van Wilt and Roberto Carr for many years of. I'm so lucky to have you, and also I want to thank my doctor. So, any questions?
Very good. We have time for 1 or 2 questions. can perhaps start to put some energy there. So in CTO, you have polarization in plane, in the superlattice, and antiferroelectricity. Polarization is 1, 1, 0. Antiferroelectricity is 1, minus 1, 0. It's perpendicular.
What?
Antiferroelectricity.
Antipolar?
Yeah, antipolar.
Oh,
It's
antipolar.
1, minus 1, 0.
Antipolar is also along 1, 1, 0 direction.
The same direction and polarization, or perpendicular to it?
Same direction, but it's not cancelled because antipolar is pushed a little bit on the positive side. So you get a non-zero polarization along 1, 1, 0 directions. But the antipolar mode is there, of course. Okay.
So I noticed that you did a separate expansion for the BTO-like phase when you did the expansion, in terms of, up to fourth order or something.
Oh, yeah,
like that. You did a separate expansion for the BTO-like phase and the CTO-like phase. And I could imagine alternatively just doing a higher order expansion around the cubic phase that would automatically take care of both of them simultaneously. Is that just too difficult?
Oh yeah, it's not. I mean, ideally it's not too difficult. we would like to take these directions in the future. We haven't think about it yet. Thank you for your.
I think we don't want to